So let me begin by thanking Pinaki and Arnab for planning this meeting. As other speakers mentioned, there have been earlier times when one came regularly to Chennai, and that has been a little slow of late. And so I appreciate the effort to sort of revive traffic in Chennai. So with that, so I'm going to tell you today about a part of work that we've been involved in for quite a while now on cyclically sheared glasses. As an aside, several years ago, I was talking to a colleague who was doing granular matter in rotating drums. And so the first time I met him, he told me about this. And the second time I met him, so I asked, so what are you doing? And he said, you know, the same rotating drums. And I said, so you're going around in cycles, are you? So many years later, I've been doing the same for the last 10 years or so, looking at glasses under cyclic shear. But today I won't talk about stuff that, hopefully I won't talk about things that many of you have heard at least more than a couple of times. But before I get going, so this is sort of, like I said, work that's been done over some years with several colleagues who are all listed here. And the part of the work that I'm going to talk about is mainly stuff that Debarga Sarkar, our PhD student, is doing, and a little bit of what Pushkar Khandare, who's also a PhD student, who's currently finishing up, is doing. And this is sort of with this group of collaborators here. Okay, so yeah, this is just to sort of get going, to say that, you know, broadly what I'm going to be talking about concerns mechanical behavior of amorphous solids. And so solids exhibit either reversible response under small stresses or deformation, or irreversible behavior for larger stresses involving plasticity and eventually failure. And understanding failure is of obvious importance for a variety of materials. So a lot of what we do know as textbook material concerns crystalline solids, but and part of the reason is that they are a large part of solid materials that we study and use, but amorphous solids arguably has a much broader diversity of contexts in which it appears, both the amorphous solids themselves as well as the failure of these solids as a matter of interest or concern. Okay, so that's supposed to be illustrated by all these different examples, including hard glasses and soft solids and so on. Okay, a particular problem that we have been sort of trying to focus on lately is illustrated this video of something that we've all done many times, which is if I were to try and break a solid, I usually can't do it in one go. So what I do is to sort of go back and forth several times. And there's some, depending on how hard I'm bending back and forth, there's a certain number of repetitions after which the material breaks. Okay, and this is something that happens because of changes in the internal structure of the solid that is not visible to the outside very easily, and this is something that historically wasn't well appreciated in the early part of the industrial era, and the lack of understanding that fatigue as a phenomenon can happen when a solid is subjected to repeated load, led to various disasters in the middle of the 19th century, including this famous rail accident in 1842, which made people wake up and pay attention. And like I said, since then, the problem of fatigue and fatigue failure has been extensively investigated and empirically sort of studied. Without commenting more about how well it is understood in crystalline solids, what I would like to sort of state without further discussion is, it appears as though for amorphous solids, the same phenomenon has a different character. Okay, and this is a reason why one should be interested, and we have been interested, and I'll tell you a little bit about that as we go on. But before moving on from this slide, here is sort of a representation of this phenomenology, where depending on the amplitude of the stress that I'm applying, there are different numbers of cycles after which failure occurs, and this is represented in something called the SN curve. So the cycles to failure on the x-axis is a decreasing okay. As stress decreases, the number of cycles increases. Below a certain limiting value of the stress amplitude, one may in fact subject the system to the solid to stress indefinitely without failure occurring, right? So this limit stress is called the fatigue limit, and this is going to come up later on. Okay, so now if we look at, okay, so what we do is to look at model amorphous solids under cyclic shear, and okay, so a lot of the work that we have done has been to look at numerical simulations of model glasses. I won't focus on this part of the work, though I will mention some results by way of background. But we've been sort of also trying to build simplified descriptions in order to identify salient features. And so one set of such works has been looking at simplified what I call single site models of plasticity, and what that means will come up in a minute, and then corresponding mean field theory to understand sort of yielding and failure, but also there is another set of work where we look at models which have spatial extent and interactions across space are a relevant part of the description, and these go by the name of elastoplastic models, and I'll show some results from these elastoplastic models. And as I go through the next few slides, what we're going to be trying to do is to sort of follow this dictum which is attributed to Einstein, that everything should be made as simple as possible but not simpler. And so we're going to sort of go from one simple description to a simpler description and see how far we can keep going without becoming trivial, right? Okay, so so here I won't say too much, because this is really not what I'm going to be spending much time on, but we do simulations of cyclically sheared glasses, and what I show here is what we are doing. We take local energy minimum configurations, which are obtained by subjecting equilibrated liquid configurations at a temperature called the parent temperature instantaneously. So you have energy minimum configurations, but because of the initial liquid configuration and at what temperature it was equilibrated, for each parent temperature, the glass that you generate this way exhibits a different degree of annealing, right? So if I equilibrate the liquid at a lower temperature and then do a local energy minimization, I have what I call a better annealed glass. Whereas if I start from a high temperature liquid and do a local energy minimization to obtain my model glasses, I have what I call a poorly annealed glass, okay, just to set the terminology. And then such glasses are subjected to either what's called athermal quasi-static shear, with no temperatures involved, or finite temperature, finite shear rate simulations. And in each case, we typically look at the properties of the system at the end of each cycle. And because there are plastic rearrangements, the properties of the system change from one cycle to the next, okay, till some steady state is reached. Okay. So this is one set of results for athermal quasi-static shear, where basically the summary of what I'm going to show you in steps is that the energy per particle of the system, which is the quantity that we monitor, depends on the strain amplitude and the initial energy when I apply small amplitudes of shear. But for sufficiently large amplitudes of shear, the amplitude by itself determines the final state that I reach. And in between these two regimes, one has the phenomenon of yielding, okay? So this is a small amplitude shear, cycle to cycle, the energy changes and reaches some final value. A larger amplitude will lead to a lower energy being reached, and it takes longer to reach that. And one keeps going till beyond some amplitude of shear, there's a qualitative change in behavior where the energy now begins to go up, okay? And this in this part of the story, depending on whether I start with a poorly annealed glass or a well annealed glass, the behavior is very different, okay? But if I go to larger amplitudes, now I begin to have final states. It's not very obvious from this picture, but I begin to have final states which don't depend on whether I started with a well annealed glass or a poorly annealed glass, but I reach the same final state, okay? All right. Now, this is a larger set of results showing the same thing as a function of the initial energy of the glass. I have a very different way of going through the yielding transition. For poorly annealed glasses, I have mechanically induced annealing before yielding happens and the energy begins to go up. And as I already mentioned, the number of cycles that I need in order to reach the final state has non-monotonic behavior and an apparent divergence at the yielding transition. And this divergence of timescales when I'm coming from above is associated with the phenomenon of reaching the fatigue limit upon reducing the load, okay? So the yielding transition as I'm describing it now would correspond to what we might call the fatigue limit, okay? Now, something that was apparent here, but I show here in a much more dramatic way, is if you look at strain amplitudes, which is my control parameter, whose values are such that eventually the system will fail, right? So all of these values that are for which I'm showing results here, if I look at the initial part of what happens for the initial cycles, I have behavior that's very similar to the case where I don't yield. So in other words, with initial cycles of shear, I anneal my system to lower and lower energies, and at some point suddenly I fail, okay? So the change in the properties of the system are non-monotonic in this very interesting way, okay, that there is initial mechanically induced annealing followed by failure. And one of the sort of the key questions to understand is why is the process of making a better glass leading to failure eventually, right? So what's the connection between the processes that lead to a better and better annealed glass and then failure happening at some particular time, okay? So, okay, yeah, so that was that. Yeah, by the way, I sought the help of my students to make some of these slides, and they've made a lot of transitions. So I hope nothing will be lost in transition. Okay, anyway, so here, this is again sort of some general background of how we might think about and model these phenomena. If you look at sort of plastic rearrangements in amorphous solids, unlike crystalline solids, these tend to be localized rearrangements like what is shown in this little video clip. Okay. There isn't anything sort of that you can say that is a priori interesting in terms of the structure of these plastic rearrangements, okay. However, what one does understand is that when there is such a localized plastic rearrangement in an amorphous solid, this leads to the propagation of stresses in the surrounding solid, and this is something that people have discussed a lot and understand. It has 1 over r to the d variation with distance and spatial anisotropy of the form that's shown here. But the basic idea is I can think of my amorphous solid as made up of mesoscopic sized blocks within which I can think of how to describe plasticity. And then anytime when there is a transition that corresponds to a plastic rearrangement in one of these mesoscale blocks, it has consequences in the form of stress propagation to the other blocks, okay? And this is the reason why I earlier mentioned modeling in terms of a single site and spatially extended elastoplastic models. So if I were to sort of focus just on one of these blocks and try to come up with a description of what happens there, that's a single site description, which ignores what's happening elsewhere in the system. But a complete description would have to include also the manner in which these different blocks talk to each other. Okay. Okay, so now from what I said, it's clear that if I'm sitting at some point in space and asking what are the stress kicks that I'm getting because of what's happening elsewhere in the system, the mechanical noise or the strength of this mechanical noise is proportional to the level of activity, plastic activity in the system as a whole, okay? That statement can be made more precise, but for now that's good enough. Okay, so keeping all this in mind, one can sort of think of what's a good description for the behavior of a single mesoscopic block, and something that has been appreciated in recent years, including, well, I'm looking at who else, but including work by Ludovic and I'm not sure about Massimo, but anyway, is that the degree of disorder or stability of the glasses is an important variable, right? So if I think of a small piece of the glass, in addition to sort of asking, you know, how it responds mechanically, or rather in answering how that little block responds mechanically, I have to think in terms of how stable the packing is, okay? So a natural language for this is to think in terms of a distribution of energies that that particular block can be in, such as what a Gaussian distribution of energies, but more importantly, to have something to say about how stable to mechanical stress a given block is based on how low the energy is. Okay, so this is sort of an energy landscape picture of an individual mesoscale block. So I can think of the system residing in different what we call mesostates, which have different energy in a stress-free condition, and then I can sort of change the strain so that the energy goes up quadratically with the strain, and at some point I'll reach a limit of stability, and this limit of stability I choose to be proportional to the square root of the depth. Okay, and when you reach the limit of stability, you hop into another minimum. Okay, that other minimum under athermal conditions would have to be a new mesostate which has at that strain a lower energy. Okay, now if all these parabolae had the minimum at the same strain value, that's one sort of simple situation, but because of plasticity, the stress-free arrangements of atoms can be at a finite strain, right? So the plastic strain that is associated with a stable packing can be arbitrary, and this is also why Bulbul was sort of talking about a stress-only description, because strain is not yeah. So, but anyway, but we are sort of thinking in terms of strain. So the correct description to have in mind is to have states that are possible for the system where the minimum energy can occur at different strain values. Okay, so here, for example, this parabola has a plastic strain that's very different from this green parabola. So at the point when the green or the blue parabola becomes unstable, even though this is a higher energy minimum, I can make a hop down to this because at that strain value, the energy of the system is lower. Okay, so this is now a description of what happens if the system is residing in one of these states, and I change the strain on the system. And with this description, I can sort of then perform the dynamics and look at what happens from cycle to cycle to the energy of the system, just like what I described in the simulations earlier. And one gets a yielding diagram which looks qualitatively very similar to what one sees in simulations. Okay, there are interesting differences, but the basic idea is, but the basic features that are reproduced are, when I start with a poorly annealed glass, which is high energy, I have initial annealing before I yield as I ramp up the strain amplitude, whereas if I sit at a very low energy state, I do nothing till I reach some amplitude at which I make a discontinuous jump. Okay, so these are qualitative features of yielding that are reproduced, except for this particular model, this is actually the behavior of the system after a certain number of cycles. There is no genuine transition, okay? Because if you wait long enough, eventually you'll find the minimum which is deep enough and stable enough that you don't then make further transitions out of it. So this sort of reproduction of simulation results is a little bit misleading, okay? But one can build on this as I described and try to do better. But at this stage, I'm going to take this already simple-minded model and make it even simpler. Okay, so instead of looking at transitions from one mesostate to the other, as I vary the strain cyclically, I'm going to ask what might happen to the system if I look at it at the end of each cycle, stroboscopically, right? And so here is some sort of simulation results for this system where I'm showing the initial energy of the mesostate that I'm occupying on the x-axis, and the final energy after a full cycle on the y-axis, okay? And without going into the details, what you can see from the color map is that the final state that I reach at the end of the cycle doesn't seem to depend much on where I started, okay? Because basically, yeah, if I take any cuts here, I get the same distribution that looks like this. And this is sort of an approximate statement. I won't go into the details, but basically what this suggests is that it's useful to think in terms of an invariant distribution that you can, think of the system as occupying, and that invariant distribution in turn I can think of in terms of a potential, okay? So a useful simplified description is to think of a random walk in a confining potential, okay? So this is what we take up. This finally didn't get fixed, but I'm going to take advantage of the transition problem. So okay, so here is now the system that I'm going to look at. I have, okay, perfect. I have a random walk in a confining potential, but the axis here is energy, right? So I'm making a random walk in energy space, and then if I'm applying a strain of a certain amplitude, it corresponds to the system being stable only for large enough energies. I've flipped the sign here. So these are deep minima and these are shallow minima. And so for any amplitude of strain, I have a boundary beyond which the system will be stable with respect to a cycle of shear. But for smaller energies, it will make a transition to a new minimum, okay? So I can therefore ask the question, how long does it take the system to reach this threshold, right? So this is now a very standard problem of first passage time, and the answers are known. So there is a time scale which I call the absorbing time, which is growing very strongly as I shift this boundary to further and further to the right. And again, I can take this model and sort of look at what the state of it is as a function of the number of cycles. And again, I get a yielding diagram which looks very similar. And once again, there is no genuine transition, because if I wait long enough, I will eventually get trapped, okay? But the way to sort of have a more realistic and interesting description is to say, even if I am at a sufficiently large or low energy so that I'm stable with respect to a given amplitude of strain, is it possible for the system to escape out of these stable states, the absorbing states? Yeah. Oh, on this side, yeah. Now this is coming from an approximation where you assume that it's yeah. It's a large first passage time result. Yeah. Okay. Okay. So that's what we look at next, which is even if I have this random walker in a confining potential and it reaches an absorbing state, the absorbing state is not permanent. It can escape out of it. Then we have to ask, what is the mechanism for you to escape out of it? And the mechanism is what I mentioned earlier, which is the stress kicks that the system might experience because of activity elsewhere in the solid. Okay, so here is an illustration. So if I'm sitting in a minimum like state like this, and this is my amplitude of this is my amplitude of strain. At this point, I'm not quite at the stability limit, But if I imagine that because of stress kicks, I diffuse in strain space, I can eventually reach that limit of stability and make a transition. Now, this diffusion in strain space, I would like to associate a diffusion coefficient to, and what I'm going to say is that this diffusion coefficient is going to be proportional to the fraction of states that are unstable to the given amplitude of strain. Okay, so here just for concreteness, I have all my energy states, and for a given strain amplitude, this is the boundary between stable and unstable states. And I'm going to ask what is the probability for the system to be in the unstable states, and that probability is going to determine what the diffusion coefficient that I will have, which will allow me to escape out of the absorbing states. Okay, so we can sort of have that picture and write a two-state description where I write the master equation for the unstable probability, the probability to be in the unstable and the stable states, and without going into any detail because I'm running short of time, what this does is instead of making the yielding transition only apparent, it actually it makes the transition a genuine transition, and it also gives you a divergence of time scales like what we see in simulations with some problems. The exponent that comes out is not the same as what we see, but we've made so many simplifications that maybe, you know, it's a little much to expect everything to come out right, but here it is. Now, okay, sorry. Then we said, you know, one thing that this two-state description will not give is any kind of a non-monotonic dependence of the state of the system with respect to the number of cycles, because yeah, the description of the system is not rich enough. So we said let's go to the next minimal description, which is to think of a three-level description where I have unstable and stable states, and I also have a new category which is the threshold states. Okay, and then I can write the corresponding dynamical equations, and when you look at the behavior that emerges, what you find is this very interesting behavior where if I look at the population of unstable states and the absorbing states, with the number of cycles, both of them actually diminish, and the population of the threshold states, on the other hand, goes up. So you have stable and unstable states, both of them converge towards the boundary. Okay, and this I can represent in this flow diagram where I have the population of unstable states and the threshold states, and what you see is this initial behavior where Pu, the unstable state population, continues to decrease, and for some initial conditions indeed I just go to 0, but if I have a large enough Pu, after an initial phase where it decreases, it turns around and goes to a fixed point where the unstable state population is finite, and this is behavior that I find when I have yielding in the system for large enough strain amplitudes, and I can sort of look at what happens with respect to the strain amplitude, how the flow of states changes, and this non-monotonic dependence is capturing what we see in simulations in a much more complicated setting, and the fact that I have several initial conditions where even for an amplitude that's greater than the critical amplitude, I can end up with an absorbing state, captures the behavior that we see in simulations of a range of initial conditions for which I don't yield. Okay, so okay, and just 1 minute. that was sort of a schematic set of equations that I wrote, but I can actually construct the same equations for the Ehrenfest model that I discussed earlier, and I get qualitatively the same behavior as the toy model that I wrote just now. Okay, and this I will skip with difficulty. Okay, so elastoplastic models reveal the same behavior of non-monotonic change that we see in simulations. And okay, let me skip this. We do see a divergence of timescales with some interesting details which I can explain. Okay, so that's the summary. So what I've described is a set of ever more simplified descriptions of the dynamics of glasses under cyclic shear, and the most simple of them continues to capture the essential interesting features of the dynamics, and gives us some insight in the form of this observation that what seems to happen with continued sort of cycles of shear is that the system evolves towards a threshold state, which then should become susceptible at some point to global failure. Okay, so with that, thank you for your attention. Happy to answer any questions.
So if you assume that strain didn't exist, can you come up with a stress-only, extract a stress-only description of plasticity from looking at the simulations?
Right.
Like, why do you need the crutch of strain?
So, no, so the point is, okay, so how I mean, in principle it could be done, I suppose. Like I said, the one thing that we do try to incorporate in this description is that there is disorder, so that I have different levels.
I understand,
right? But then, yeah, then you have to say.
For example, let me ask you: if the plastic strain is not uniquely defined, then is there a stress-strain relation? Like, what's going on?
No, the stress-strain relation is not uniquely defined, but once you fix the plastic strain, it does become uniquely defined. That's the whole point. But that plastic strain is an additional variable in your description.
You're introducing sort of what I would, yeah.
Yeah, but anyway, no, I don't know how to do it with a stress-free way, but this is sort of a construct which takes care of the fact that the strain is not a good variable by itself.